have you start?
Yeah, I start to record. Yeah.
Awesome. Okay, great. Hello everyone. Welcome to the episode 6 of the AFib seminar. Today we have Jonas coming to talk about interesting about model with the recurrent depth. Just a little bit of background about Jonas. Jonas is an ML researcher in Tübingen, Germany, where he leads a research group in safety and efficiency aligned learning. Before this, he's been a couple of times in different places, including University of Maryland. Comes to efficient learning, he studied how we can build systems that do more with less, with averaging techniques to recursive computation approaches that extend model capabilities, with a particular interest in how the systems reason and whether we can enhance their reasoning capabilities while maintaining efficiency. And how do we build mechanisms that let these models learn to be intelligent systems? And of course, his research is also the intersection of efficiency to safety. Can we build this model that reason well without sacrificing safety? Can we design systems where intelligence and safety reinforce each other? So with that, Jonas, please take it away.
Yeah, thank you for the detailed introduction. Yeah, happy to be here. I'll give this talk and really, oh, you raised your hand.
Yeah. Yeah, I see.
In general, really, you can just ask questions all the way throughout the talk. Otherwise, I think it will be a very long thing of me just saying lots of things, and then in the end, people might have forgotten the question. I'm really happy to stop in the middle to like talk about things, and so if there's something in the middle, you can probably just raise your hand or just talk or post on chat, and I might see that. And I think that will work out. All right, yeah, let's get into it. Yeah, so this talk is what's so interesting about models with recurrent depth. And this is really the question that has been keeping up for a while, or I'm trying to make this talk to convince you that recurrent depth is interesting and what that means and why I think it's especially interesting from a scaling perspective. Can I actually click though? Oh yeah, I can. So first off, most of this what I'm going to talk about is based on this recent preprint that we've made, which is with a bunch of great co-authors from the University of Maryland and Lawrence Livermore National Labs. And we have a paper, and we also have code for everything, and we also have the model open source and also the data, although I'm still uploading some chunks of data. Okay, so what are a few key concepts here? Let me also put this away. So first, what's test time compute, right? We thought this paper is about recurrent depth, but we'll come to this connection to test time compute very quickly, so I'll talk about that as well. Test time compute really is, for me, defined by improving the performance of a machine learning model by using more computation at test time, right? Or using more computation for inference. And this is, of course, a very general paradigm. There's lots of approaches towards that, and many ways you can do test time compute. But we'll see in a bit how it makes sense to think about recurrent depth and recurrence or adaptive computation in general as a form of, or maybe for me, like a very general form of test time computation. Also, to get this out of the way, what do we define as reasoning? I guess that was also in the title. Right, for me, reasoning really is this idea that while maybe you believe that these models can only pattern match to things, as long as the model can pattern match to abstract concepts, such as maybe a meta strategy or some logical operations, really to abstractions, right, to planning, to plans, instead of just memorizing really concrete facts, then a model that can understand these patterns and generate these patterns is not so different from what we would call something that is reasoning. And I think that's really motivating as an idea that why can these models do reasoning and how would they be able to? And what we've seen a lot over the last half year is we've seen a lot of verbalized reasoning, right? We've seen lots of models that improve with chain of thought. Maybe chain of thought we've seen for a few years now, but now we've seen reinforcement learning approaches that really make models that have great chain of thought and can really reason through lots of things in their chain of thought, right? This is an example. I think this is Cloud 3.7, and it's like a trick question about how to load an aircraft, and the model starts out and it's like, oh yeah, I could put the items in like this. Or I could, attempt number 2, I'm going to do it like this. I'm going to check it like this, and it says, oh, this doesn't work either. Let me try another arrangement. Attempt 3. it keeps on doing that, it keeps on doing that, it keeps on trying different arrangements, thinking about it until it finds a valid arrangement of these parts in this aircraft. Actually, this took 2 minutes on the 3.7 API, right? But ultimately, this model can reason through a very complicated reasoning problem like this, and then find a solution that satisfies these constraints by running more and more computed test time here, right? The model is actually fixed in size. It's just using its size better than before. It can answer harder questions by, in this analogy, running more compute and thinking longer. And that's really interesting, right? Because now we have the second axis of scaling. We do already know that we can make these models smarter by making them larger and training them on more data. But over the last half year, we've really seen great ideas on how to make these models really think longer, right? And this is a second axis in which we can scale model performance. We can still make models larger, we still do, right? But now we can also do this on top of what we're doing before, which is quite interesting. But so why is this necessary? I guess there's a part missing here. Right? Why do we actually need chain of thought? Why can't the models get this right? What's interesting is that because these models are fixed depth transformers, chain of thought actually is a requirement. Because if we think about even very simple multi-step reasoning problems, for example, here's the sentence, John's father is Mike, Mike's father is Tom, John's grandfather is, well, of course the answer is Tom, but how would the model get there? Interestingly, if we think about a 4-layer transformer, then we kind of see that for a 4-layer transformer to get the answer right in one token, 4 layers really would be necessary. Because we'll use the first 2 layers to make this connection from John to Mike, and then we connect Mike to Tom, and then Tom to the grandfather. Right, and here we sort of like in this diagram, which I, by the way, I've stolen from this paper from Wang et al. Understanding how transformers do multi-step reasoning with matching operations, which I think is very interesting. Right, here we see this like 2-hop or 2-step reasoning process. And we can easily imagine that if the reasoning process is a chain that's more complicated, then if we want to get this right in one token, it's just not possible with 4 layers. Or it's only possible if we do if we like squeeze it in somehow, maybe we try to parallelize it in ways that work some of the time, but not always, right? But on a principle level, we need really a certain amount of depth to get a certain amount of multi-hop reasoning robustly right. But now that we have chain of thought, we can sort of like do this differently, right? We can first figure out, okay, John's father is Mike, and we can put this into a different, we can like just run this chain of thought sort of like horizontally, right? And this way we produce more and more intermediate representations, and we can increase the depth of our graph through these intermediate representations in a normal computational transformer. This is why, maybe to me, why we need chain of thought. But what's interesting about this whole business is that if you think about it, it really doesn't seem optimal to put all the reasoning into words, right, in this way. Because as we've seen before, right, we have these very long reasoning chains that run for maybe here hundreds of thousands of tokens, and they all consist of the same operation, right? The model attends to all previous tokens, it produces the next token, it decodes that, and now the reasoning is slightly different because it now can attend to 1 token more, and so we just keep on running this through. And this really implies to us, like, maybe it's just much more optimal to do continuous reasoning, which is the idea that maybe we should just move this entire reasoning chain into the model's representation space. So we shouldn't actually decode 1,000 times in these intermediate steps, but we should just keep the entire operation in the model's hidden space. And this way the model could, and we're still in this motivation part here, right? But right, we think about this, that the model could still then, for example, follow multiple tracks in parallel, right? Or even have like very different reasoning patterns, just because it can do everything in this high dimensional vector space, and it's not so constrained as before. But so why do this with recurrence in depth? Why particularly this, right? Maybe that's the next question. And maybe also, what is recurrent depth? In my definition, really recurrent depth is really a model that recurs in its depth, right? So it reuses its layers or its parameters, its other subcomponents to create, a deeper or a shallower model by using more or less of its layers or more or less of its compute by reusing its compute. And this really is like such a foundational or basic idea in ML that this has been invented and reinvented over many generations of ML researchers many times. But you might know this if you maybe are from like the 2017 area, maybe you think this is universal transformers. Maybe if you've gone through the conferences over the last year, maybe you think this is looped transformers. Maybe you think this is representation recycling if you come more from the like AlphaFold direction. Maybe you think this is really like all Alex graphs are an answer of adaptive computation time. Maybe you think this is equilibrium models, diffusion models, iterative refinement, implicit neural nets. Maybe all of this really is like, I think the earliest reference is some things like the feedback mechanisms like in Hopfield and Amari. But really, the idea to just reuse the same parameters and to like recur is very foundational to machine learning. But still, like the key question was like for our paper, right? We obviously didn't invent recurrent depth, right? The idea is like, how can we scale it? How do we get it right for language modeling? So that we can actually train a large language model to do reasoning with recurrent depth. That was really our motivational question. Right, and recurrent depth is really interesting now in this connection to test time compute. Because if we just train a model with recurrent depth, and I'll talk about how we get to retrain it, but I think you can easily imagine that we just train on normal internet web text. And because the intermediate steps are in vector space anyway, there's no supervision on those anyway, but we find that actually we don't need any supervision on them. We can have a model that learns how to use these intermediate steps without supervision, which is interesting, right? Because now we don't need something like reasoning chains out of R1 or something, at least in the way we pre-train the model so far. What's also interesting is if we scale the model in depth in this way, then we have a different complexity scaling to if we scale the model in token dimension, right? Because if we run quadratic attention, then we're running quadratic attention in the sequence dimension, but we're not quadratic in the depth dimension. And this is, I think, pretty interesting. What's also interesting is that the recurrent depth models are just naturally smaller, right? They have fewer parameters, they use them more often. And this is interesting for a bunch of inference applications and a bunch of like ML engineering reasons where it's just very inconvenient to have large parameter stacks. And I'll talk about this more a bit later. Right, but maybe a bit more generally, or a bit more maybe motivationally, these recurrent depth models really are compute heavy, right? In the way that they have fewer parameters, but they use them more. And I think this is a very interesting paradigm, right? Because it's the idea for me that what's like a good prior for a model that reasons? In this, like, from this previous definition of reasoning, where I think reasoning is something like learning patterns, right? Learning abstraction, learning logical thinking, which really is like, now this is a model, if it can do recurrent depth, then it's easy for the model to learn iterative algorithms. And a lot of iterative algorithms to me have a lot to do with reasoning, right? And because the model has fewer parameters relative to the amount of compute we use, it's also harder for the model to memorize. And that's an interesting prior. Separate from that, we have lots of good data on more toy scenarios on where this can really work well. For example, we have these scenarios, this is from Bansal and Schwarzschild and Borchner, Huang, Goldblum and Goldstein, a paper on using recurrent depth models for maze solving. And that's quite interesting because on mazes, we quite well understand hardness. Right? We can easily understand here, this is a very simple maze, it's 13 by 13, and a model can learn to solve it. But what's interesting is if you train a normal neural network on these kinds of mazes, you really don't have any hope of using this model for any other kind of larger maze. But what is shown in this paper, if you train a recurrent depth model, which has a good prior to really learn an algorithm for maze solving, if you learn this recurrent depth model on this maze size, then you actually get a model that also does other mazes, right? It actually, you can, at test time, you can give this model a much harder maze and it can still solve it. And even further, you can even make this a massively larger maze. But in this toy scenario, these people have trained this recurrent depth model, and it really has just learned the algorithm for maze solving, right? Because ultimately, this is a dead-end filling algorithm. It's not super complicated to learn this, but it is interesting that like a fixed depth neural network wouldn't have the right priors to learn this kind of algorithm, but a model that recurs in depth has the right prior and does learn this algorithm. And then it can just solve mazes of this type. Still, this was a few years ago, and for a long time it wasn't so clear how to do this well with transformers, or how to really scale this with transformers, and how to really train very large models that can generalize in depth with recurrence. Right, there have been a few more transformers that are using something like weight sharing, where you do repeat parameters, but we'll talk a little bit more about the difference between weight sharing and really generalizing to fewer or more iterations. So what we propose in this paper is to use an architecture that looks a bit like this. And here's interesting, why do we call this paper, why do we call this latent reasoning? And lots of people have been arguing that this is latent reasoning because it's in this hidden space. But actually, I think for us it was a bit much more down to earth, that this is just latent recurrent depth because there is a latent part. So this is the architecture of the model, and there's three main components. There's a block of layers that we call prelude in blue, which is non-recurrent, which embeds the inputs, right? Then we have this recurrent part in green, which we repeat many times. And then we have this coda in red, which is again a few blocks of layers, which again are non-recurrent, right? And this is a bit like a latent diffusion model or some other latent model, right? Where we actually do the computations in this latent space that we project into using this prelude. So that's why it's a latent recurrent depth model, really. And this really seemed to help us in efficiency, and it connects interestingly to lots of analysis work of real transformers, real fixed depth transformers, where people often show that the first few layers of the model do something different or do some sort of hierarchical embedding or some sort of like modification of the representation. And then the next 50 or 60 layers, maybe of like a Llama 3 model, just do computations. They look up things. They can be interchanged. They can be like moved around. And then the last few layers again are important because they really unembed and produce the next word. And with this latent recurrent structure, we have a similar setup, and we found this to be really helpful. Yeah, this actually, I think I said this already, is actually, each of these blocks doesn't have to be a single operation or a single transformer layers. For us, actually, these are 2 or 4. Question. Do you want to say your question, or I can also read it out? I can read it out, no worries. The question is, the recurrent block expands the model in depth dimension. Does it mean a singular thing with mixture of depths? It's actually a hard question to precisely answer that. Mixture of depth works in a different way, but maybe it has a similar goal, right? What is very different here is that in mixture of depths, to me at least, in that original paper, it's really about efficiency, and you still have a fixed number of layers, right? And in a very basic sense, you just use fewer tokens per layer. So in that sense, you have more or less compute per layer, per token, which is related to this. But it is different, for example, that like mixture of depths, maybe I wouldn't call that compute heavy. Like the number of parameters is still the same. You're just not using all parameters for all tokens. Although that's maybe also normal to a normal transformer. Yeah, actually, I've been like a bit back and forth on how to connect this to mixture of depths. I think it's just a different angle. It's not so clear how to do a precise connection there. Without the help of KV caching, can this be faster than original decoder-only transformers? That's also really it's somewhat hard to answer the question in general. We'll come a bit more to inference optimizations later in the talk. For now, I think a good way to think about it is if the alternative is running a very long chain of thought, then in a very long chain of thought, you have quadratic attention. Whereas here, if you order it differently, then you don't actually have quadratic attention in the same way if you just want to produce one more output token, right? Because you just have more compute linearly if you have more depth. Next question. Did we run applications without the product block? We did. We could have been better actually at putting these in the paper. So the paper config has maybe a very honest problem in the paper is that it's already very long. And a lot of these things we did on small models. Like we ran about like several hundred like models of about like 100 billion parameters and 10 billion tokens. And on those you can really quickly see that it's much more optimal, or like you can train to much lower complexity if you have this sort of prelude setup. But as we'll get to later, ultimately we only have one model at scale. And for that model, maybe I would have wished for more compute to do this exact ablation. But on the final model scale that we talk about most in the paper, we don't have so much room for ablation. So we'll come back to this later, right? Because yeah, ablations at small scale do show this works. And now let me get to where I was. Yeah, two interesting things here as we look at this longer. So one is that we have this really, in this recurrent depth literature, this is also called an input injection, right? Where you actually see that the inputs to these recurrent blocks are not just the previous hidden state, which are here, the hidden states are all S, but the input to this recurrent block is also the embedding. And this looks a bit, maybe looks a bit wacky to you at first, but it's interesting to think about this from different angles, and this actually is pretty critical to make a stable recurrence. So one way to think about this is that if you don't have this input injection and you recur for a very long time, then what you basically have is you have a dynamical system where the data is only given as a boundary condition. And this is not very stable. And if you want a system that actually depends on the data, and we do actually want this model to depend on the input, right? Then we need it to actually connect to the input, right? So you have this sort of like residual connection, or this like, right? This is really a skip back to the input here. And another way to think about this is also that with this kind of setup, you can think about the recurrent blocks as a generalization of gradient descent. In the way that like maybe you have some initial state that's S0, and here also the initial state is random. And then as you do gradient descent to learn something, you keep on doing steps like from S1, 0 to S1 to S2, you keep on doing a gradient descent. And of course, you do a descent step with respect to the data that you actually have, which is E. So I think it is very natural that these two have to come in here. Also, yeah, I said this before. What we also found a bit helpful was this idea that the actual initial state should be random. This is based on prior work on path independence, and we found this to help a bit to stabilize the recurrence. What's interesting is that now that you have this random state, you start with entirely random states and you keep on refining it, it looks a bit like a diffusion model, right? And on some diffusions, this actually is very close to a token by token diffusion model. Interestingly, trained by a very different objective, and also quite different from maybe what you've seen now is that making more like other modern language diffusion models, which really work in different ways and really don't do this token by token. But there's a connection here, right, in the sense that both diffusion models and this are both recurrent models in the way that they reuse parameters to refine a prediction. Before I go to what that means, yeah, this is not really layer skip, but I'm going to talk about how this model can exit early, and exiting early has a lot to do with layer skipping, right? Well, maybe what's interesting thing about is that if you have a model that can exit early, then you can do less compute, but you can't do more compute. And with this different architecture, we want to do both. We want to do more compute and less compute. input injection, does it provably help with stability? Depends on the definition of provably, but I really think there's this paper from Anil et al. About path independence. That's really a good source on why you would need input injection and what this does to the stability of a dynamical system. In the paper, we also link this idea that from a convex optimization perspective, I think I actually can't go back here. From a convex optimization perspective, you need the input injection so you can learn a monotone operator that depends on data, and that is necessary to have this connection. But maybe that's a bit non-obvious to people that don't love monotone operators. So I think the path independence paper is probably a better reference.
Where's the reference to the convex optimization in the paper?
I think there's a footnote somewhere on a page.
I see it.
That relates to Bauschke. Right, but the idea is, again, this is related to this other analogy to dynamical systems, right? That if you want your operator to be simple, which would be in convex optimization, this means it's a monotone operator, it needs to be data dependent. Otherwise, you have to make a more complicated non-convex operator, or non-convex, maybe the wrong word here, but non-linear, non-monotone operator. Right, what does this mean? That we have this recurrence, it really is something like this, right? Where on a token by token level, you run this recurrence, right? You have your model, it has a current prefix that you've pre-filled, and now you want to generate the next token. So what do? You run this recurrence. And here I'm showing you the first 6 PCA directions, which is maybe some idea of what the model is doing, right? So here you see the model is having a random initialization, also in as PCA directions. And then as we run the recurrence, it settles into some end term behavior. And this doesn't always have to be a fixed point, it doesn't always have to converge. But here we see that the end term behavior is always stable. It's always here, for example, here's a limit cycle or an orbit. Here, but we just made the word A, and now we're working on 3. In the sentence, I think the sentence is Claire makes a 3-egg sandwich. Right, and so really there we go, token by token, we run this recurrence, and then we project out again, and that's our next token. And I hope I can get out here. Oh, that's one too far. So what's interesting about this is how we train it, and how we train this is actually. Let me first talk. Sorry, I made some adjustments to the slides right before the meeting, and I think I skimmed one slide here on how we train this. So let me first talk you through how we actually train this model, and I'm going to talk about alternatives. So how do we train this model? What's interesting is that we train this model based on prior work in this idea of recurrent depth, also this Bansal and Schwarzschild paper. We train the model by unrolling the recurrence for a random number of steps and then backpropagating to the last k steps of this recurrence. And if you think about this a bit, it's a bit of a funny objective, right? Because we don't actually train the model to be good at a certain depth. We only train the model so that at a random depth during training, if we decode from that depth, it should predict the next token. That's really all we do, right? Our objective is entirely based on unrolling randomly. But what it turns out is that the model, this just turns out to be very scalable. And we find that if we have a good distribution of random steps, so I wish I could show you a picture, but it is pretty much a Poisson distribution with a very heavy right tail, which means that most of the time we just sample a few steps, maybe between 10 and 20, but some of the time we sample 30, 40, 60, 80, 100 steps, and then we predict the next token. And this way we really train a model that can exit early, but we can also train a model that can handle more compute, right? And it's interesting to think about this from this perspective of next token prediction, because at some point you've trained a model that can always predict something reasonable after 4 steps. But now you keep on training it, right? Your gradient is still not 0. You're still not perfect at predicting the next token. At that point, you really have to push more compute into more recurrence, which you do see now and then, right? And at some point, the only way to further improve the model is to push more computation into this recurrence. And so why is this like, why do I keep talking so much about this training objective? If you compare what we've done to a number of other recurrent depth models, you see that the training objective really is a big differentiating factor. So for example, if you go to something like universal transformers, there you wouldn't train with randomized depths, but you train with something called a halting module that would tell you when to stop iterating and when to do, and then you would train based on that. But we found that really hard to do because it's really hard to train this halting module at the same time as training the whole model. And if you look back into the original universal transformers papers, then you also see that like this works very well for small things, for like copying, pasting, but it's much harder to scale these universal transformers. Another thing you could do is you could train an equilibrium model. There, the idea is that you actually run the iterations always to convergence, and then you differentiate through the fixed point based on the implicit function theorem. That's also possible, but it's a bit harder to scale this in compute and to do these inverse Jacobi things correctly. So we just didn't end up choosing this. It could also work. Interesting is also that maybe like more a classical weight chat model, where you just say, oh, I just want to do 16 steps, and you just always do 16 steps. You can do that, right? Something like Albert, maybe it was a BERT model that has done exactly that. But if you just always fix the number of steps, then you train a model that is only good at a fixed number of steps. And the model actually turns out, if you just train for a fixed number of steps, the model actually can't extrapolate to more steps. It actually then reduces the performance again. And you can't use it for fewer steps, because then it's also bad. So really, running a fixed number of steps is not the solution here. But these other things maybe. Also interesting is that if you compare this now to the diffusion model, a diffusion model is even a different training objective, right? Where you have a target hidden state, and you train to denoise this hidden state, which is interestingly not unrolling, right? It's not implicit differentiation, but it's some sort of surrogate objective. And these are like three main groups here are surrogate objectives, implicit differentiation, and unrolling. These are three ways to train these recurrent or these operator systems. Maybe I'll do some questions before we go further. Do you run into exploding vanishing gradients when training on many steps? Yes. In the way that like we really have to be careful with parameterizing this recurrence in the right way so it doesn't blow up or it doesn't fall apart during training, which is like a partially unsolved problem yet, and I'll come talk a bit later as we talk about these larger scale runs where we really see this happening in practice. Yes, input injection also improves normal transformers. Interestingly, there are some papers on doing this. For example, there definitely was one variant of the non-GPT speed comparison where there was a version where you also just inject the input into the values of the attention. That also worked very well for those transformers. I'm not sure what the exact reference. Maybe someone knows what paper that is. Value injection, something like that. But let me keep on going here before I get too much off track. Right, so actually, the real thing is like, so we've seen recurrent depth models before. Maybe this is all just motivation, right? And you're just not sold on all these motivations. Like, why would I care about this, right? We also weren't really convinced about this, right? Because we can train many, like 100 million parameter, 10 billion token models. They all work great. They're all really exciting prototypes of machine learning. But it really doesn't convince us nowadays that this really does scale, because many of these things that work well on the small scale don't scale. So to be more convincing to ourselves, we set up a larger target architecture, which we call this Hugin 3.5b model, which we named after a random bird in Norse literature that is just incidentally named Thought in English if you translate this name. So this model has 8 layers. So the first 2 are non-recurrent, then we have 4 in a recurrent block that we keep on iterating, and then we have 2 more that are non-recurrent. We tie the embeddings so that we have 3.5 billion parameters in total. So this model has about half of its parameters in the recurrence and half out of it. And we targeted about like 1 trillion tokens, so we really would train a large model. And we had about, we're going to use compute a bit equivalent to a 32B parameter model, so not a small amount of compute. But I don't know, we're trying to see can we actually train this kind of model to be a semi-competitive language model? So it can really, in the base sense of the word, can this model language, but can also be good at reasoning? And then we had some intermediate questions about actually getting the compute for that. That took us a pretty long time. Yeah, these are the small scale input injections. That's a good reference in the chat. So we set out to train this model, and so we trained it on this data mix of a mix of generic text, of code, of scientific text, a lot of math in there. Although we really didn't have so much compute to really hone down on this data mix. So this is what we trained on. Then, though, we did get some hardware. So because we applied for this Insight program, which I by the way can recommend to applying to. Insight is a program of the US National Labs. And so they gave us compute in Oak Ridge, at Oak Ridge National Labs, where they have a very large AMD cluster. I mean, they have some few others, but they gave us compute on this one. So we were very happy to use it. And this is a cluster of 8-way MI250X cards, which are previous generation AMD cards. Pretty uncharted territory though, very quickly, right? Because you could look at this cluster setup and it's very nice. Infinity fabrics everywhere and like nice connections in technically. But it's really hard to make use of most of these AMD features. And it was really a bit of a harrowing experience to train a model here. But maybe I'll skip all the fun parts of that and just say that we did actually train a model. And we trained this model on 4096 AMD GPUs in about 21 segments. So this is a Slurm system. You only get segments of about 12 hours. So we trained on 21 segments of 12 hours with a constant learning rate with warm-up. Why a constant learning rate with warm-up? Pretty much just because we actually weren't sure how many segments we would get. So we just queued the system, and because it's a warm-up of constant learning rate, when we get a new segment, we can just continue training from that. This is why we trained it like this. Interestingly, it's also because the model is only 3.5B parameters, we run a lot more compute, but it's still small enough that we can do DDP. And it's kind of a particularity of this really model architecture, right? That it's so compute heavy and so, but so light in parameters. And a different way to think about it is also that we probably couldn't have trained a larger, more conventional model on this machine so well, because we had lots of trouble with the interconnect on this machine and with the speed of interconnection. But now with our smaller model and more compute, it actually was a pretty good fit for this machine. And this is also why we trained it here in this way. Then, I mentioned this before, does it ever blow up? Interestingly, we had 2 failed runs of like the first 50 billion tokens that didn't really work. And I'm going to talk about this briefly. Because what is interesting is that, so on small scales, you can vary many things about the architecture, about the optimizer, about the whole setup, and everything you vary still kind of tracks. It still kind of works. You can do RMS norm, you can do AMP parameters RMS norm, you can do layer norms, you can change the blocks around, you can have this or that different, right? And on the small scale, all these kind of work, and they're all kind of trained to a good complexity. But on the large scale, so we had our first run, which was in orange, where we had a maybe relatively large learning rate, and lots of things that we just kind of had, right? So the first one had no embedding scale and had no learned adapter, where adapter is this part that connects the embeddings and the previous state. And this run, you see it in orange, it first, get my mouse pointer, right? The fun first goes down, looks good, but very quickly it just plateaus around like a loss of 7, which really means the model just doesn't learn something better than a linear model. And then we kind of scrambled around, and we first went around to change our block structure, because we had initially trained with a sandwich block, but we went back to a more normal pre-normalization layer because it's more established at scale. And we also flipped our adapter to be learned. And this was the second run in green. And interestingly, the second one is kind of tricky because it first looks like it works, like the loss goes down, looks nice, right? But then you look at this recurrence chart, and you see that on this recurrence chart, there's just one line in green. And what this chart is showing is the validation perplexity for different recurrence steps. And that there is just only one line in green just means that this model has just learned to ignore the recurrence entirely. It is just not using it, and that's why the performance is the same whether we run one recurrence or whether we run 64 recurrences. And that's also why the model is plateauing here, because we're pretty much just training a 4-layer transformer with extra steps, or with more complications, right? It's actually not a very good model. And then we scrambled around once more and did some more initial testing. And then we trained this main one in blue, which now it does have the embedding scale. It does have a lower initial learning rate. And it goes back to our sandwich structure again that we had validated on the small scale. And this run did work, and you see here we see very early that it splits up in recurrence, but here you see the validation perplexity for a recurrence of 1, here for a recurrence of 4, and here you see the validation perplexities for recurrences of 8 to 64, which are sort of like logarithmically getting closer to each other. So these are the models that we trained, the three, well, not three. The model we trained is the blue one, right? That we actually trained. And with this initial scaling slide, I really want to talk about. So because this is a bit of a new architecture, it's a bit unclear how to do this right. I think like all these issues, we kind of fixed them, but it's the thing where I imagine that if someone sits down with a pencil and paper and actually really thinks about the initialization and the stability of this operator, then they'll just say, oh, that's kind of a stupid initialization that you picked there. You should have done it like this, and it would have been stable. But we kind of didn't have the manpower to run through this like initialization theory here, so we kind of winged it, and I guess it worked. There's a question in the chat, did we use checkpoint averaging? Do we have a plot with the original run and with checkpoint averaging? I do not have a plot for that. We only did checkpoint averaging after training the whole thing. Okay, so long story short, we had this model architecture, we had this compute system, we figured out how to stabilize it, and after that it was pretty smooth sailing, and we trained for about 800 billion tokens. Not quite the 1 trillion that we wanted, but at some point the year was over and our compute was done. Results. So the first result, very fast, this figure really was like the sign of life, because it wasn't so clear like beforehand that this actually would work. For me, this figure is really like the key like sign of life figure of this paper, because it's showing you that if you train this model and then you run it on JSON-K chain of thought, some benchmark, right? This is generative JSON-K. If you run the model and you always do 1 step, you can't solve JSON-K. If you always do 4 steps, you're pretty bad at JSON-K. 8 steps, still pretty bad. But if you do 20 or 32 steps, you're very good at JSON-K. Right? So the model really has learned to use this recurrence. And with a few recurrence steps, it can't solve JSON-K, but with a sufficient number of steps, it can. And interestingly, or maybe even more interesting, is that for different eval sets, for example, for OpenBookQA, this behavior is different. For example, for OpenBookQA, which is more of a, I think the benchmark is a bit badly named in this modern way, because it's a closed book benchmark. You just ask the question about some science topic. But for this benchmark, you pretty much see that after about 12, you get some performance that's close to random at the start, and you spool up with 6 or 8 recurrences. And after about 12 recurrences, you're kind of done. You can do more recurrence and the model is stable, but it doesn't continue improving. And this is quite interesting, right? Because this task really is knowledge heavy. And here, at some point, you've either retrieved this information, like either you know the science fact about planets, or you just don't know it. And then you just stop improving. And you can also see this for Arc Challenge, which is a bit of a mix of questions about knowledge, but also a bit trickily worded, where you see this behavior is a bit in the middle, where it plateaus somewhere here. And what's also interesting is to think about this model is only 3.5 or 3.6 billion parameters, right? This initial state. But as we run this recurrence, we really just make transformers slow again here, right? We really train a model that materializes many more parameters, or uses the parameters as if it was much larger, right? If we run our 3.6B model for 64 iterations, we could have run a 103 billion transformer for the same number of flops. This would be flop equivalent to the sum of that size. Interestingly, it wouldn't be memory bandwidth equivalent, right? A 100 billion transformer model would have much more memory bandwidth, which really is a bottleneck in inference. But we use that many flops. And in this way, we really are doing test time computing, right? We're running this model for many more test time compute steps, or many less test time compute steps. Doesn't prenorm sandwich norm cause early recurrence convergence? Does the fact that they have quickly separate? The scale of the short path will grow linearly. That's possible. For prenorm, maybe. For the sandwich norm, because it is sandwiched in the particular way that the paper does sandwiching, the recurrence actually is very stable. Like the scale of the short path is actually bottlenecked by the last RMS norm, so it's always the same scale. But for prenorm, I'm not so quite sure whether prenorm is worse in the way that it grows linearly. The sandwich norm we've made here doesn't grow linearly. Next question. If more recurrent steps do not improve accuracy, can increasing the width of the model improve accuracy? Yeah, I do think so. Right? If we make this model even larger, either by putting in more non-recurrent layers or making the recurrent part wider or larger, we could memorize more things and we could know more things. Recurrent definitely will consume memory bandwidth too. Yes. Yeah. So I should be more precise about memory bandwidth. While if we had a 103 billion parameter model, we would need maybe several GPUs to store this model. If you only think about bandwidth from like to and from cache, this model is 1.5 B parameters in the recurrence, which is far too large to keep in the L1 cache. So there's still lots of memory bandwidth needed there. That is true. Yeah. Memory capacity is a much better way of saying it. But also, right, this model also really saves on memory if we're doing distributed training across nodes. This was this previous point, right? That really, at train time, we saved a lot of communication bandwidth by training this kind of model. So interestingly, maybe it surprised, mostly to my surprise, it actually turned out not to be a terrible model. Don't get me wrong, it's not DeepSeek R1, it's not but also we didn't have that much compute, right? But the model is surprisingly capable for this being the first training run, right? Because we only did this one training run. You see it, this was the blue chart. That was the one training run that we did. And the model is kind of, if you compare this to other open source models, maybe similar compute levels, then you can see if you compare this, for example, to something like the first generation OMO model from last year, then you're a bit similar in performance to this first OMO 7B model, which was trained on 7 billion parameters and 2.5 trillion tokens. Right now, our model has 3.5 B parameters, 0.8 trillion tokens. It's still a bit of a apples to oranges comparison, right? And you also see that if you look at more improved data recipes, especially in OMO 2, which came out a bit earlier this year or end of last year, that's still a much better open source model, right? But I think it's so surprising how good this model actually is with this setup. And what's especially interesting is how good the model is at GSM-8K. So what's interesting is that the model is particularly good if you do GSM-8K or GSM-8K train of thought, where you hit like something like 42% accuracy, which is much better than most of the previous open source models up to OMO 2. And this is interesting, right? Because the model really is much better on GSM-8K. And actually, I don't have a slide on this, but it's also much better on code benchmarks on, for example, on human eval. It's much better than you would think from this chart. So it really scales a bit differently than the fixed depth transformers that we're used to. And so one way we can really hone down on this apples to oranges thing is that, so one thing that we did do is we trained a baseline twin comparison model where we trained the exact same architecture, the exact same data, the exact same setup. We just always set the recurrence to 1. So this was effectively always an 8-layer model with the same number of parameters. And we trained both of these models, or actually maybe we trained this big one for 800 billion But so we trained this fixed depth comparison also for the first 10,000 steps. Here, this is 180 billion tokens. And so what's interesting is if we do this early comparison, right? So this is the fixed depth baseline. We compare this to the recurrent model, then we see that both of them are at the start are not really great. Right? They haven't done a lot of compute yet. But even very early in training, the recurrent model is much better at GSM-8K. It's actually 5 times better already at this task, right? And this is the exact same number of parameters trained for the exact same data chunks. It's just that this model is recurrent and it can use its recurrence to do more computation, right? And someone, for example, has argued here that, yeah, this model has 8 layers. It just can't solve GSM-8K. But that kind of is the point, right? This model can use more depth and this way can do more recurrence. What's the longest recurrent depth sample during training? So on these charts, I'm still a bit simplifying. These are all per query level recurrences. This model runs 4 recurrences for all tokens. This one runs 8 for all, 16 for all, 32 for all. We've run this up to 64 and 128 for all. And for example, like on this chart, you see it going up to 64. And you can do more, but it really flattens out here, right? This is really a sigmoid curve, where eventually you don't benefit more from the recurrence. Yeah, it's really an unfair comparison, right? The recurrent model is much deeper. Yeah.
I think that, I'm wondering, like, what is the longest recurrent depth you observe during your training, right? You have sample from a distribution during your training, right? So, after how much expression you can do during the inference time on the recurrent.
Yeah. So, so at train time, we have this, we sample from this Poisson distribution with a heavy tail, which has a mode around 20 and lots of weight around 20 and a median of 26. And then at test time, for a bunch of benchmarks, we actually saturate earlier than that. We're around like 20 or something, right? You already see this actually saturating earlier. But for the harder benchmarks, especially for GSM-8K chain of thought, we actually peak around 64 here. Although here, you do flatten out as you go outside of this range. So in some ways, I'll just come back to this later, this is still not magic. And the thing that we wanted with the mazes, where we really can do arbitrary computation and be arbitrarily good, the model didn't really do this. There's like several benchmarks, like especially GSM-8K, where the model is actually best at 64, which is 32 steps, or depending on how you count them, 40 steps out of the training distribution, but it's still not magic, right? It doesn't actually go up like this. It saturates. And I think that's an interesting question, like, is this based on the data? Is this based on the architecture? Or could you train this model differently? Or could you like fine tune differently? So you'd have a different behavior, right? Because on many, like maybe actually on most of the pre-training mix, it makes sense that you should saturate, right? Because on maybe most of the web text data, you have to be good by knowing the data. And eventually, once you figure out that that's kind of question, there's no point in running more recurrence through most of these examples, right? And so I think that's quite interesting. It's not so clear yet how to get all these sigmoids, right? Or maybe this is a fundamental limitation of these models, that they have these kind of sigmoids charts. Yeah, right, more data on this. We do see that, right, here also now, we looked at most of these already. What's kind of new is the human eval, right? We do see that on these harder tasks, we can use more compute and we end up like increasing more with more compute.
Hi, I have a question with respect to the training part, which is, right, you have different depths for different kinds of, you sample depths for training, but the thing is, how do we make sure that the ground truth is always the same? Like we can use the same ground truth for depth equal to 1 all the way until 32. I wonder how can we make sure this is a reasonable setting?
Really, I think like a design goal of this was really the simplicity of it and the scalability of it, right? During training, we just do next token prediction at a random depth, and we just don't give this as a target, right? But I do agree with you, especially in settings where we do know that some data is hard and some data is easy. It would make a lot of sense to set different depth targets, right? To say, oh, this is easy data, you should do 4 steps, or this is hard data, you should do 32 steps, right? But doing pre-training, this is just not so scalable, or at least not, to me, it's not so clear how to do this in a scalable way during pre-training. But it is then, but I do think it's a very interesting question, right?
Yeah, thank you.
So far, there have been no recurrences chosen at test time, yes. So far, this chart simplification is just, here's a number of 32 recurrences. And we'll get into test time adaptivity later. What's also interesting is if we look at the performance on these benchmarks as we scale pre-training, you see that we haven't really saturated pre-training. We do see that the 1 recurrence or the 4 recurrence really have stopped improving. So the model really has stopped doing more depth here, or doing improving on like 4 recurrences, and it improves slower on 8 recurrences. But on 32 and 64, this is almost maybe still linear. Probably almost, right on this point, it's not so clear how to extrapolate further how this model would do if we had trained for maybe 1.6 trillion tokens or for 4 trillion tokens. It's not so clear when this actually would fall off. Yeah, let me get quickly back to this question about model comparison, because I do think it's a hard question, right? Right, if you compare, here we compare these models by number of parameters. And so of course this one is much deeper, but it's much deeper by design, right? If we had trained a 32-layer transformer model, I would hope it would do GSMK better, but it's not so clear how to trade these off, right? And this idea that one of the models is maybe depth limited on some task really is fundamental if we think back to this idea of the multi-hop problem, right? If you say that maybe for GSMK, maybe I need 32 layers, then maybe then my point is that, okay, so I train this model with 32 layers, but maybe it can't solve, I don't know, maybe it can't solve Hendrix math with 32 layers. And now you're saying, oh, maybe you should have had 64 layers so you can solve Hendrix math, right? And maybe then I ask for this complicated multi-hop problem that requires 102 hops, right? And then you would want a model that has 102 layers. If we just keep on scaling layers like this, there is still this limit to the architecture that on how many multi-hop problems we can solve. Where I think it's really motivating to think about recurrent depth as a way to scale depth, right? And to have a model that can do more computations with the parameters that it has trained. What's also interesting here is that we also have these findings that as we compare to context length, we actually find that if we give the model, here this is our challenge, if we give the model more few-shot examples, here for example we give it up to 50 few-shot examples, then we see that the saturation point actually increases. Right, like for 0 shots, the saturation point is somewhere around here. And then for 1-shot examples, the saturation point is somewhere here. And then for 5 shots and 25 shots, it's somewhere around here somewhere, right? So as the model has more data in its context, it can do even better with more recurrence. Which is interesting, right? Because this is the same model in all 5, right? This is just this one model we trained. We're just using it differently. We're giving it more or less context, so maybe more or less things to consider in the answer. And its scaling behavior and recurrence is different. So what really is the model doing? That's to me like a super interesting question, right? What actually is happening under the hood? So one thing that's immediately interesting is that we can look at convergence rates per recurrence step per position. So what I'm showing here is a target sentence, and the sentence here, you just see a sentence, it's like a part of the system prompt, you're blah, 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 right? And what we actually see is if we compare the hidden state, so the last step of the recurrence, so like the current step of the recurrence, you see them here going from 1 to 64. If we compute the difference of this vector to one that I computed at step 256, so much further into the future where we think this has settled down, then we see that the difference to this end state is not always the same. It's actually drastically different. So for some tokens, the model converges much quicker than on others. And this is pretty exciting, right? Because we didn't train for this. At training, we always gave the same batch, or at training time we sample a batch, and we randomly assign this whole batch a certain number of recurrent steps. So maybe there's like no reason for the model to differentiate like this in convergence, right? This doesn't help doing pre-training. It just seems that naturally, just by training like this and training at scale, the model naturally learns this sort of like input specialization, where on some tokens there's doing more compute, especially on tokens that are hard. But these are tokens that we do know that in standard transformers there's often compute that's relevant here, right? We often know that there is compute maybe on something like a dot or a colon where the model has to think about what comes next. This actually matches with what we see for transformers. Here's a comma. Right, so it's really interesting that this just arises from scale, that the specification arises even though we didn't train for this. As a reminder, why didn't we have a stopping criterion during training? It is actually, a stopping criterion during training is a bit like a universal transformer halting module, where we train this halting module during training. But it just seems very hard to train the model to improve on all sequences, and at the same time train this halting model to exit early. It's possible that we just couldn't get this right to train these two at the same time, but we just found this randomized depth approach to be much more scalable than these previous halting module-based approaches, where you train the stopping criterion and the model at the same time.
But couldn't you have done it without a halting module and just been like I guess like just pick a threshold for your like what your tail divergence between two successive steps, or just be like when this like just literally a fixed threshold and then just train that way, or?
Yeah, a fixed threshold would have been easier than the halting model. That is true. Haven't considered that. It would be a bit more annoying for parallelization reasons. Like a separate reason why fixed depth is nice is also because then you can do the same amount of compute per token in the sequence, so it's nice to parallelize that. But yeah, you could have done the exits, right? You could have also just cut off, right, and run the same amount of compute for every token and just cut them off earlier. That would have been possible. Maybe that's worth trying. Yeah, right, so because these are high-dimensional vectors, it's quite hard for us to analyze what we're doing. So what I'm showing you next will be mostly these PCA things where I take these vectors, I put them all together, I compute the largest PCA directions of this entire collection of vectors, and then I plot the first 2 or first 6 of them. For example, here you see them in token space. Here you see the first 2 PCA directions on the X and Y axes and the token position in the Z axis. And this pretty much is the sequence I just showed you, right? Where here you always start in dark blue around the center at random, right? And then the model in this first part, this is actually all the system prompt. You see that the model always goes in this direction, in these 2 PCA directions. And later it goes into other directions, so like fans out, but often you see that like tokens that relate to each other also fall in related positions in this latent space. But what you also see already here is that there's some swirlies here, right? Like sometimes it actually doesn't always converge. And so what's really exciting for us is that what end term behaviors actually emerge from this very simple training objective. And what we find is that for most tokens in the sequence, it's pretty straightforward. We initialize randomly, and then the recurrence runs, and it converges to some pointed latent space. For many tokens, it just looks like this. But interestingly, for a number of tokens, especially related to reasoning or to things like sentences like he makes or she thinks, or often numbers, we find that the end-term behavior is often this kind of loop or orbit, where the model keeps on building this orbital structure. And we see this like here, this is the first 6 PCA directions, but you can even see this up to like, I think we looked at up to like the first 40 PCA directions. And that's really quite interesting, right? Because we do know from other work that models often use these frequency-based approaches, for example, to implement addition. We know that fixed depth transformers also try this, but it's much harder to analyze in fixed depth transformers because each of the layers has maybe more of a different hidden space, or it doesn't have to be similar. It has to be similar only in the sense that it's a residual stream. But here it's much more clear to analyze these hidden states because they're all on one trajectory. And what we also see is that we also have these, maybe a third type, which are these sort of sliders where the model sort of slowly slides in one direction. And these are also interesting because we're not so, to be honest, we're not so sure what these do. But what is interesting is if you have these sort of sliders, then you can do things like counting. You can actually count how many recurrences you've done so far if you compare from a different point in the sequence to where this point is currently at, if you have these sort of sliders. Right, so to me, it's really surprising how much of this complexity just emerges from this very simple training objective and just training this model at scale. And we have these different interbehaviors where it's really not so clear how to really optimally analyze them yet. Right? We have lots of tools to analyze internal model states, and they already are maybe really required here to really understand what this model is doing. Other advantages of recurrence, right? I started out way a long time ago. I'm actually not so sure how long I'm talking already. I'm telling you what's interesting about recurrent depth. And so far we've talked all about test time compute, about like trying to scale, about doing more computations. But what are other advantages of test time recurrence or of recurrent depth models in general? Maybe the first one, which I really just like, is recurrent depth just simplifies speculative decoding. Right? Speculative decoding is the idea that you have a small draft model that you use to draft the next few tokens in your autoregressive generation, and then you can just verify them with a large model. And that's a bit annoying because you have to self-speculate, which you have to train for. You have to like exit. There's some ways to do self-speculative decoding, but maybe the best thing to do is still to use an n-gram model or to have these smaller models that you train specifically to do speculative decoding. But with this model, you can just do it. Right? You can just run the model with a few recurrent steps to draft the completion. You could even make it hierarchical, and you can just verify with more steps. And you can even reuse the computation that you did for the few steps. You can even reuse that later because it's just the same model. It's just running more or less compute. And I really like this example because it really shows you that you could do different things if you had this different architecture. And some things that are maybe a bit more harder or require some more research and standard fixed depth transformers are just much more trivial for this model. Right? And then secondly, so we do know, we looked at this, that the model can do different convergences. But what we find is that we actually can just use this, this behavior of the model to do zero-shot early exits. Because what we do is we pretty much just do the simplest possible thing, is we just compute the KL divergence of the probabilities at each step. And if the KL divergence is small enough, then we exit. And so we haven't really tested this extensively in the paper. This was really more of an addendum that I just found interesting that this can actually work at all. This actually does do something. But what's interesting is that for different domains, you actually see that if you exit by like a fixed KL threshold, depending on the domain, you have these different exit behaviors. For example, for something like these harder domains, maybe you exit often around like 15 or 20. Whereas for something like high school mathematics, you can exit early from many tokens in your sequence, which is quite interesting, right? Because we didn't train for these different charts. We just trained with this very simple objective. There's a few more of these in the paper, right? Because we can also simplify things like KV cache sharing, and we also simplify things like continuous chain of thought, just by running this model in different ways, which I think is quite exciting. And also, right, like while this kind of works, I would also think that now that actually the model is trained, it would be super interesting to see what a trainable or like a trained adapter or a trained exit module actually would do right now that the model actually is doing things. Because it's very encouraging that it can do a passable exit already at zero shot. So finally, conclusions, takeaways, and the future. So one thing that I want to talk about also a bit in the seminar is how would this connect to maybe your current neural nets or to efficient sequence mixers? And what I find pretty interesting is that if you have an efficient sequence mixer, maybe something like Mamba 2 or maybe Delta Knight or something, for some operations, to my understanding, you do require depth to match quadratic attention, right? You just can't probe everything that you can probe if you have had a quadratic attention because you just don't attend to all previous tokens, right? You actually only have a linear recurrence in sequence dimension. But if you have a model that can actually run in depth, right? We can actually recur in depth. Then you can do many more probes, even with linear recurrence or linear attention, right? You can actually maybe this is a bit of a stupid example, but if you would recur sequence length many times, then even with a linear attention, you can just probe every previous token. And I think it's quite interesting to think about this interconnection of how or what way something like efficient sequence mixing would be connectable to something like this sort of recurrent depth, because I think they would go together quite well, but I haven't quite figured out how this would work or how this would be helpful. Oh, I think there was one more question about the previous state. Yeah. Okay, but that's also the answer in chat. You can just run the recurrent model for fewer steps to draft tokens, and you can just verify them by running more steps. Then the second future thing I find super interesting is maybe I've said the words compute heavy too much in this presentation. But right, if this model really is compute heavy, and maybe there's also a few others that maybe it would also be compute heavy, then what's parameter heavy? What's the sort of like the matching pair to this? And to me, that really is a mixture of expert models, right? Or maybe more generally, really it's like all types of memory implementations. And I think it's a super interesting question to think about if this maybe is more the computational block of the model or the computation part that does more computation with the parameters it has, then how can we best combine this with something a mixture of experts, right? And there's some prior work on this, especially on the something like MOE-UT, where you still have a fixed number of recurrences, but you do have the MOE in there. And I think that's super exciting as a direction, because you kind of try to build a system where you have some parts that you really specialize from memory and parts that you really specialize from computation. And you can do these interesting interplays of MOE and recurrence and depth. For example, you can do things where in a normal fixed depth of normal MOE, you could really only use every layer expert only once, right? You could either use that expert in that layer or you don't use it. But if you have recurrence, you can actually query these experts many times, right? So you can maybe be more efficient about how you use this memory-heavy, parameter-heavy system, which I think is pretty interesting. Final conclusions. So we were really surprised how far we could take this paradigm, just pre-train these models very differently. And it was pretty exciting or maybe pretty harrowing at times to actually train this model. And this fully actually still is the only model that we trained at the scale. But it worked surprisingly well for the first of its kind in this way. There's a big question around, or maybe this is maybe a fool's errand, right? But this is a question because if we compare arbitrary extrapolation and compute, maybe if you compare this to something like the reinforcement learning based verbalized general thinking models, maybe like something like DeepSeek R1, there also we can run the model for much longer and think long. But those models also don't improve indefinitely with more chain of thought. Eventually they flatten out as well. And this model maybe is similar, but I think it is a very motivating question to see how we could push this curve further, or how we could get this model to really do this thing that we saw in mazes, right? Where we could really extrapolate to arbitrary amounts of compute and be arbitrarily good. There's a side question on what tasks would actually require that. Because there's actually very few tasks where we can make them arbitrarily hard in this way. But I think it's a very interesting question around this module, right? Like how can we get further extrapolation out of this model? Then there's lots of questions about how to actually fine-tune, post-train this model, right? I think there's a number of interesting questions that we are maybe currently trying to figure out, but we also don't have any idea on how to really do this. And I think it's interesting because there's a number of ways you could fine-tune this model very differently. Because you have this recurrence. And then the final question is, right, is this really complementary to scaling model performance? And also, how can we make a better apples-to-apples comparison to chain of thought, right? Is this actually necessary? Maybe not. Maybe you should actually just do chain of thought in token space forever. But I think it's interesting to think about the idea that maybe you could just do all three of them, right? You could scale compute in this hidden dimension, and maybe this way you would especially improve on problems where it's not so easy to verbalize the answer. Maybe something like spatial planning, maybe things like that we as humans do more by just thinking about them in our head and about the structures. Right? Like maybe something about like rotating shapes. Right? Maybe you would do these ideally in this axis of scaling, and then you'd still verbalize something that can be verbalized, for example, like math, in the token dimension. And you would still scale model performance just by making the models larger. And we really have to see how these things interact and how they would fit together. I think it's a really interesting question for the future. Yeah, with that, I'm at the end of my presentation, and I'm happy for more questions. Do you have any thoughts on having 2 iterations stacked after one another, or nested ones? I have not thought about nested ones. There's a few previous papers. There's also one from Apple where they do a weight sharing with nested blocks. At least based on my intuition on how transformers work, this doesn't make so much sense for language, because in language, after you've done the initial embedding, language is not so hierarchical, at least to my understanding, that you could actually have these different layers or these different groups of recurrences. But something, for example, if you had a multimodal model or a model really about vision, there I think it makes much more sense to have multiple stages that have their own recurrences. Ultimately, this is one other paper about that's called the inner thinking transformer that actually has multiple stages. So maybe multiple stages could be good. I haven't figured out the exact apples to apples comparison. Other questions?
I know you studied a little bit, but what do you think the dynamics of the final state look like? Do you think you could represent that as a dynamical system, maybe without having to use attention modules, or do you think it's very closely tied to attention?
I mean, because we use attention in these blocks, these are dynamical systems that depend on attention as a computation. Right, you can really maybe this is a discrete dynamical system, right? It just runs attention. It just runs, if you run this infinitely long, it really just isn't a dynamical system. Attention is just a part of its operation.
Right. I guess I was just wondering if maybe the effect of running many layers would reduce the fact that attention has these trivial dynamics, but maybe that's not really the case.
I haven't thought about that so much. Yeah, I guess I don't know. That's a good question. Does performance saturation with number of steps relate to the model dynamics converging to a fixed point or limit cycle? It could be happening in intrinsic dynamics. I do think that's a good question, right? Or maybe to answer it first at face value, yeah. Right? Performance saturates because the model has converged onto some end state behavior. But what we've also seen is that when the model converges, depends a lot on the actual question being asked, how long the context is, how hard the question is. So somehow, when it converges and to what state it converges really seems to determine that it saturates. And I guess I'm not sure I would call this transient dynamics, but maybe a different way to look at this is to me, this is actually very related to energy-based models. I'm not sure if that's an obscure reference, right? But it really to me relates a bit to the question of some problems are easier, so it's easier to converge to a low energy state, and some questions are harder, so it takes longer to converge to a low energy state. But they all eventually converge to a low energy state in this dynamical system or to this energy-based model, right? And the analogy here maybe is that this recurrent depth model, if you think about the recurrence as learning a gradient of an energy, which it doesn't quite do, right? But in this analogy, then you would have this relation to energy states that maybe it would take you different amounts of time to converge to low energy states, depending on how hard the question is or how much context you have. I hope that answers the question. And I'll go to the next one for now. Complex computational patterns. Are the structures incidental emergent properties, or might they suggest the formation of implicit computational language? That's a good question. I'm not so sure how to approach it. I do think that these patterns are not accidental in the way that we do know that orbits relate a lot to addition in fixed depth transformers. There's this paper by Neil Nanda about analyzing modular addition. Or maybe modular addition is a bit begging the question of why it would be a circular operation. But so I do think it's not quite incidental that these structures emerge. Why they emerge like this? Unclear. And would they be more pronounced, or would it be possible to analyze them better? I think that would be super exciting. If we didn't increase the dimensionality further, would they be more pronounced? Maybe. The dimensionality really is quite large already, right? While I've only showed you the first 6 PCA directions, these are 5,280 dimensional vectors, right? They really are quite high dimensional already. And by the way, they are 5,280 because the AMD chip has 110 SMs, and that's why it's 110 times 64. I think it's 5,280 or something like that. Anyway, if anyone wants about the funny number of hidden states, it's very AMD specific. It's 5,280. Slight digression. Would there be a principled way to distill recurrent depth into an RNN over sequence length? I mean, I guess all methods that have come out over the last year have been quite exciting about distilling normal fixed depth transformers into recurrence. I guess those methods would still work. I'm not sure how well they would work or what they would do, but I guess they would still translate. I'm not sure whether attention is core to these dynamics. I don't think so. But it's really hard to analyze, to be honest. Could recurrence help with precise scaling up of algorithms due to precision loss or error accumulation? So regarding soft attention and language generalization, for this models, I'm not so sure. There is very interesting related work where this is described as loop transformers. And for loop transformers, in some small scale settings, people show very convincingly that loop transformers are better at length generalization. So that does seem to be an indication. We have really not tried this for this model. I'm not sure how this model length extrapolates. But there is these papers on that loop transformers are better at length extrapolation. Maybe they would apply here as well. Regarding soft attention, I do think the problem here is the same, right? That no, maybe I guess it could sharpen attention over the depth dimension. Maybe, but maybe as a first step, I guess this model would have the same soft attention problem that the normal transformer has, because we don't really do anything in the sequence dimension, right? The model is a normal transformer in some way, in the way that it goes token by token in the sequence dimension, and all the computers in the depth dimension. The architecture seems to favor learning algorithmic reasoning rather than storing large amounts of factual knowledge. In practical applications, how do you think this architecture balances reasoning capabilities and knowledge storage compared to traditional architectures? That's a good question. So the only thing we really have to go on so far are these benchmarks that we've run, and we can see that on some benchmarks that we think are more knowledge heavy, it doesn't do so well compared to what we would expect from the size. And on some benchmarks that are very knowledge unintensive, we think it's surprisingly good. But we really haven't probed how the model would balance this. And I think it's really something where, like, I think a good experimental design and a good way to create data sets that trade off reasoning and knowledge storage could really help here. I think there's some experiments in the physics of LLM series that I thought would be related here, right? Where like really the idea is like, can we like really nail down what the knowledge is that's being stored right now in some stage or some step of a very like controlled training setting? I think it would be super interesting here to see how this model would trade off knowledge storage versus computation. But yeah, I don't know right now. Further questions?
Yeah, you mentioned, can you hear me?
Yeah, I can hear you.
All right. So you mentioned earlier that you might run into exploding vanishing gradients, and you promised to later talk about that. I'm curious about your thoughts. Could you elaborate?
To me, this section about the first two runs at scale not converging is the same problem as exploding gradients or vanishing gradients. Oh yeah, I really skimmed over that, but let me scroll back to that a second. So while I don't have something about vanishing gradients, what we did plot is this hidden state correlation. Hidden state correlation is the correlation of the hidden states of all tokens to each other. Right, and if the model has a hidden state correlation of 1, then the model predicts the same token for every position in the sequence, and it really has collapsed in its representation, and it's really a bad model. And hidden state correlation has a lot to do with vanishing gradients, because if you predict the same hidden state for all tokens, you really have stopped learning the sequence, and you really cannot get out of this again. And this is interesting, right? Because if you have a recurrent operation, you're not really fully in control. If you have a recurrent operation that's a bit bad, and you recur it for too long, and it sort of like converges in this recurrent state to a collapse, and then you compute a gradient from the back, you might not fix this problem. So to me, these are related to vanishing gradients, but maybe that's more of an obscure and not a direct comparison.
Cool. But did you look actually at the gradients and how big or small they are?
Yeah, they are smaller in the early layers, but right, it's a bit of a harder question because we actually care a lot about the actual gradient that you would get from maybe recurrence 4 to the gradient signal we get for recurrence 8. And then at train time, we actually just put those together, right? Because we update all parameters, and we just update them no matter, right, with like 4 steps or 14 steps, signals coming in together. So this really, so like vanishing gradients really was a design consideration, and the model we have trained is set up in such a way that the gradients are not zero into the prelude, so it actually does learn something there. But maybe we haven't done the full careful analysis maybe that we could have done if we had more time.
Cool, thanks.
Invariant transformers concepts emerge in middle layers. I do think, like for us, this fact was the motivation to try this latent architecture. The idea that we have this abstraction in the middle layers. I'll go back to it. I'm not sure it's necessary, right? That would have the abstraction in here, in these middle layers, and that we could have the embedding and the unembedding in these non-recurrent parts. So this really was a motivation for us to have it happen here, and I would kind of hope that the abstraction will also emerge here, but we haven't probed that. I think we're a bit too small of a team to try all these analysis questions that have there's a large body of very cool analysis that have been done for fixed depth transformers, and some of them are super exciting here. We just don't have the manpower to try them all. The Coulombs system is very similar to a DQ model of truncate backward. Yes. Let me go back to my slide here, right? DQ really is an equilibrium model. So for us, this really worked at scale, like this unrolling objective really worked quite well at scale. And so we scaled this up. And equilibrium models are a bit harder to do right. Maybe that's actually on me and not on equilibrium models. I think it's conceivable that there would also be a good scalable way of doing especially these, the ghost part. What's this ghost thing called? There's this approximation of the Jacobi that's necessary. That could be very cool here. We just haven't tried that at scale. But I could think that would work as well.
Phantom gradients, is it?
Oh yeah, yes, phantom gradients. Yes, not ghosts. I think it could work here as well. Yeah. What's the idea about reconsistency problem as a diffusion process? Yeah, I think it will be interesting to think about like a diffusion, right? Because so the unrolling still has the idea, the problem, or maybe the downside that you actually have to unroll the model. So you run more compute through it. And for diffusion, you really have no higher order derivatives. You really just have the model. You predict a noise, you denoise a state, and you're good to go, right? It's just one step to the model in some way. And I'm not so sure how to scale this well because then at some point then we're just doing a continuous language model diffusion, which is a bit hard to get right.
I think there's no continuous language diffusion, but I think the advantage of diffusion is that during training, it's not need to unroll the layers. It only need to do such things during inferences. So
Yeah.
This
This would be a big advantage. It's not so clear how to do it well. What we
Yeah.
did try was we tried with our objective to inject noise during training on the trajectory, right? So that we inject a lot of noise on the early steps and less noise on the later steps. But this really didn't do anything for us for the small models. They just trained the same way with the noise than without. So we just didn't end up doing that. That's a remark in 3.1 about that. But that could be because we trained still with the unrolling objective. It could be that if we trained with the noise and the diffusion objective, then it would make much more of a difference. Oh. Yeah, I think, yeah, I hope that answers the DAQ question. Have you, I think, oh yeah, other questions about that. Have you considered the separate prefilling and decoding? I haven't considered it.
Yeah, because for previous chain of thought, we mainly do it in the decoding phase. Yeah, because that for feeling that you know the last token, that you can use it to generate the next token, and yeah, you know every token. So that and another thing is that I think that the computation of the prefueling is already computation bound, so that maybe during, for example, recurring if we're doing it multiple times, the problem is that it will still increase the inference time. Yeah, so I just think that how about maybe just enabling doing some recurrent for the generation stage, because that it has more into reasoning and computation. Yeah.
Yeah, that's a good point. I really haven't tested that. I think we actually tested it most often just the other way. Because the prefilling stages are computation bound, right? We often, for example, for the adaptive compute, we always run the prefilling stage for a maximal number of recurrences. And then as we do the generations, where we spend so much time, there we did the adaptive exits. But I guess what you're suggesting would be a bit of the opposite, right? That you're basically running only like 4 or 8 steps in the prefilling, and then allow the model to take many more steps in the generation part. Yeah, that's interesting. I haven't tried that. That's very tryable.
Yeah, because I think another thing
that's
is
a good point.
Yeah, for the prefueling, you have to because that the input text is fixed, so that you do how many computations the next token is fixed. But for the generation, if you do more computation, maybe you can skip some intermediate steps. So I just think, yeah,
that's a good point. Yeah, thanks for the question and for bringing this up for the comment. Yeah. Have I missed any questions? What do you think about the recurrence, about the relationship between recurrence in time with temporal structure and recurrence in depth? By recurrence in time, dynamic test time training paper iterates on current tokens multiple times. Something like test time adaptation, to me, is also a form of depth recurrence, right? In this very broad way of thinking about it, right? That you're doing more computation at test time. I think what's interesting about test time adaptation is that in a way, it's because you're doing gradient descent on some objective at test time, you're reusing your model's layers without having to train a recurrent model. So that's an interesting connection. But I'm not so sure how to fit them together, how to trade them off against each other. But test time adaptation is maybe related here. There's another question. what are your thoughts on figure 15 in the appendix? Is that this figure? Let me scroll. Is it this figure? Otherwise, you have to remind me which figure of mine is figure 15 in the appendix. Yeah. I mean, what this figure really is just showing is that, so early on, so here you have the sequence going from the 0th token to the last token. And all tokens start out at random, right? So random, they have a random PCA direction, they're in the middle here. This is normalized. And then we see that they specialize. And this part, this first part is here we see this is all the system prompt. And we do see that at least in these first two directions, they seem to determine this in some way. And we see later that often tokens that are close to each other in the sequence, and maybe they also carry similar information, they also like fall into similar parts of this latent space. And I think that's quite interesting. Of course, this is a really, really cramped down two-dimensional projection of this 5,000 dimensional latent space. So I'm not so sure, like I wouldn't take away too much from this, right? But I do think it's interesting to see what they are doing maybe globally here. Hope that helps. What do you think is happening with the divergence of direction? Yeah, I do think that like mainly this is right. Like this direction is just all the system prompt, and this direction is the user message, and this direction is the answer. Why they fall in different PCA directions? I'm not sure I'm qualified to say, or I'm not sure I know. But I do think it's interesting, and that's why I include the chart. Yeah. Final question, but I think otherwise we're probably way over time. I have no idea what time it is. But I think we'll stop presenting here.
I think there's a more question. Yeah, one more. I think the last one.
Oh, 1 point. Yeah. Related to the prefill, how would this work for non-causal attention? I mean, in a basic way, you could just do this for non-causal attention. I think it would just work in a similar way. Probably the most related to that is something like Albert, which is this weight-shared BERT model, right? So Albert maybe is still weight-shared, so it doesn't really extrapolate to more steps or fewer steps, but it is a non-causal model that reuses its parameters. And that seemed to work quite well for them, at least back then when people were really excited about BERT models. But yeah, thank you for all the interesting questions. It was really exciting.
Yeah, I think that therefore we can end here today. Yeah, thank you very much for Jonas and all the audience. Yeah, I think it's a very nice. Yeah, and there's a very promising direction. Yeah,
we'll see.
Yeah,
Answering so many questions.
Yeah, thank you for having me. Have a good evening or a good day.
Yeah, have a good evening.
Bye.
Let's stop recording.